It's math time with Heinz. It's math time with Heinz. Math time.
Everybody, on today's show we discuss what it means to be a solution to an equation and review some properties that we've been using since kindergarten. So this is the beginning of Algebra 1, Unit 1, Lesson 1, where we look at equations and inequalities, and we start off with some nice easy review and some basic vocabulary for this entire unit. So we have an opening exercise here. Determine if the following are expressions or equations. So at some point in your mathematical career, you've talked about what it means to be an expression or an equation. So take a second, pause the video, and see which of these you believe are expressions and equations. So hopefully you paused the video and you're back now. So what makes something an equation is it's a statement of equality. It's saying these two expressions are equal. It is a mathematical sentence with these equal signs here in it. So this first expression, this first statement is 2 times 4 plus 5 is equal to, this is an equation, because it has the equal to there, is equal to 4 plus 9. Well, statements can be true or false. My name is Mr. Hines. That is a true statement. I live in Florida. That is a false statement. Statements have true or false truth values. It's either a true statement or a false statement. So here is 8 plus 5 the same as 13. Yes, this is a true equation. It is a true statement. This next one just simply states 2 times 4 plus 5. I don't know what it's equal to. It's not a full sentence. There's that verb equals to, is equal to, is missing. So this is just an expression. There's no equal to. 2 times 1 plus 5 is equal to 1 plus 9. Well, this is definitely an equation because it's got the equal to there. And let's see, is it a true statement or is it a false statement? 2 plus 5 is 7. Does 7 equal 10? Last time I checked, 7 does not equal 10, so this is a false statement. That equation is false. It's an equation, it just isn't a true statement. This last one says 2x plus 5 equals x plus 9. Well, I see an equal to, so it's definitely an equation. But how do I know if it's true or false? I've got this variable x in there. I have no idea what x is. X could be a number. X could be anything. X could be anything. I have no idea the value. I have no idea what x is, so I don't know if this equation is true or false. When we solve an equation, we're figuring out what value makes it true, but right now I have no idea what it is. It is just a statement, 2x plus 5 equals x plus 9. It's not necessarily a true or false statement because we don't know what x is representing. So we call a value a solution to an equation, and this is basically what we do when we solve equations, is we find the solutions to equations if when I substitute it, if when I plug it in for the variable, it makes the statement true. So number 1 here says show that x equals 4 is a solution. Show that x equals 4 is a solution to this equation. Now, in theory, you all passed 8th grade because you're sitting in my Algebra 1 class, so you already know how to solve this equation, but it's day 1, so we're going to take it easy and not actually solve an equation today. So how do I show that it's a solution? How do I check if something's a solution? We use some substitution. We're going to take x equals 4 and play everybody's favorite game, plug it in. Take 4 and plug it in wherever you see the variable x. So I have 4 plus 2 minus 3 times 4 minus 4. Does that equal 6? I have no idea if it equals 6. That's what we want to figure out. So we can be nice lazy mathematicians, or we could follow our order of operations here, but you could throw this side into your calculator. I have 6 minus 3 times 0 equals 6. 6 minus 0 is 6. This is a true statement. This is a true statement, so x equals 4 is a solution. So x equals 4 is a solution. Por qué? Why, you may ask? X equals 4 is a solution because when plugged in, we get a true statement. 6 does equal 6. That is a true mathematical statement there. So x equals 4 is a solution. Is x equals 6 a solution to this equation? Justify your response. So justify is a verb we're going to see a lot in this class. Justify means do math. Do some kind of math. You don't need to write me a sentence. You don't really need to do much. Do math that supports your answer. Actually answer the question. Is it a solution? We need to say yes or no. But actually, we're going to have to do math, and we're going to justify it with some math. So pause the video and see if x equals 6 is a solution by using that idea of substitution. If I plug in x equals 6, if I replace x with the value of 6, do I get a true statement? So pause the video and see what you get. So here's what I got after I plugged it in. I have 7 minus 2/3 times 6 equals 6 minus 8. Well, let's start with the easy side. That gives me -2. 2/3 of 6, oh, fractions, oh goodness, but thank goodness there's a calculator hopefully sitting in front of you. 3 equals -2. That's not looking so good. 3 does not equal -2, so my answer here is no. X equals 6 is not a solution. Why is it not a solution? Because 3 does not equal -2. But it didn't ask me why. It just asked me to justify. Justify means do math. Did I show the math that supports my answer? I did, so I'm good. X equals 6 is no. X equals 6 is not a solution. So we could show that x equals 1/2 is a solution to this equation here. We could take x equals 1/2, plug it in. But please just trust me, x equals 1/2 is a solution. Determine the property of real numbers that justifies why this equation, this is going to be our original, this is going to be our start. Why each of these equations has the same solution set. So what property am I applying to this starting equation to end up at each of these steps here? So we need to look at how did that change? How did that equation end up here? Well, it looks like they cleaned this up. This changed here. They took the 2 and did what with it? Oh, this is that property we've been learning about since 3rd grade. This is the distributive property. It's the distributive property where they took the 2 and distributed it to all the terms inside that set of that parentheses there, because it's multiplication over addition. I'm multiplying over that addition. They took the 2 and distributed it into that set of parentheses there, to that binomial. So the distributive property is going to be following us for this entire course. I promise you that. It is going to chase us every single day. Not every day. I'm over-exaggerating there. But the distributive property is essential to basically half of what we do in this algebra class. And even in Algebra 2, the distributive property loves to make an appearance, which is why you've been learning about it since the 3rd grade. Let's go here. We'll go red. How did I start with this equation and end up here? Well, I have 2 times, x plus 4 became 4 plus x. It looks like order changed. It looks like order changed. Now take a second. Think about order changing. What property did we learn about previously that says I can change the order of addition? Oh, that's the commutative property. And the commutative property says that I can change the order in which I add things. I can do x plus 4, or that's really the same as 4 plus x. This is the commutative property of addition, because I'm switching the order of addition. Addition is a commutative operation. I can do 4 plus x, or I could do x plus 4. And in doing so, I'm not changing the solution of the equation. It's still the same equation, it just looks a little bit different. So whenever I change the order of things, I'm using the commutative property, either of addition or multiplication, depending on what operation we're changing. So let's look at the commutative property of multiplication. Let's slide on down here to the purple one. I took this x plus 4, this is one chunk, that x plus 4 times 2. Whereas up here I was doing 2 times x plus 4. So this order changed again here. The order changed, so that's the commutative property. The commutative property of multiplication. Multiplication is another commutative operation. I could do 2 times 3. But you might say it's 3 times 2. I'm going to get the same result. It doesn't change the value of whatever expression, or it doesn't change the solutions of the equation that we're working with. So these properties should be somewhat familiar to us. This is hopefully a review. And finally, let's go down over here. I didn't actually touch the left-hand side. The left-hand side looks pretty good. Oh, but what happened here is I grouped these guys together. I changed the grouping. I didn't change the order. 2 times x plus 4, 5x, 6x. The order is still the same, but I'm changing the order of operations. I'm grouping these together. And that's the associative property. That's the associative property, which actually isn't that important, and it is important, but we use it all the time, and we don't really know that we're using it. That we're changing the grouping in the order of which we do addition or multiplication. This is the associative property of addition, but there does exist an associative property of multiplication. The key thing with the associative property is it has to deal with parentheses. I'm changing the grouping, I'm changing the order of operations here. I'm not changing the order of the numbers or the mathematical objects we're working with. Here I actually changed the x and the 4 over here in the commutative property land. But over here, no one changed where they were. I changed the grouping by adding in or changing the parentheses. So the key thing with the associative property, hopefully you remember, is it has to do with the grouping of the terms, not the actual order of their placement in the expression or equation. So consider this quadratic equation. This equation looks a little bit more complicated than things we've worked with before because it's got that x squared, which makes it the quadratic equation, and we basically solved these in March. So this is a little sneak peek of what's happening for about the entire month of March. We solved quadratic equations. And this quadratic equation has 2 solutions, x equals -5, or x could equal 1. It has 2 different answers. We're not used to that, but that can happen. Sometimes equations have more than one value that make them true. So the first thing I ask you to do is verify that x equals -5 and x equals 1 are solutions to the equation. Well, how do I check that they're solutions? Everyone's favorite game, plug it in. We want to plug it in and see that we get a true value. So you're going to have to do 2 different substitutions. Once you're going to have to plug in x equals -5, and once you're going to have to plug in 1. So pause the video, take a second, see how you do plugging in. See if you can substitute those values in there and see what you get. So let's plug in -5. -5 squared plus 4 times -5, does that equal 5? I hope it does. But here's the thing. If you're using a graphing calculator, that -5 better be in parentheses. But you're smarter than your calculator. Our mathematical abilities are so much stronger than our calculator because we all know when we have -5 times -5, the product of 2 negatives is always a positive number. So 25 minus 20 equals 5. 5 does equal 5, so it is a solution. What about 1? 1 squared plus 4 times 1, does that equal 5? 1 plus 4 equals 5. That's the true statement to me. So they are solutions. This equation has 2 different solutions, -5 and +1. They both make it true. Should these be solutions to this new equation? Well, let's look at this new equation here. X squared plus 4x plus 6 equals 5 plus 6. Well, how does this relate to this original equation I have up here? x squared plus 4x equals 5. It looks like I added 6 to both sides. I added 6 to both sides. And that's a legal move in mathematics. We can add the same quantity to both sides. This is called the addition property of equality. This is called the addition property of equality. And the addition property of equality says I can add a 6 to this side of the equation, but if I add the 6 to one side of the equation, I have to add the 6 to the other side. Otherwise, I change the solutions. Did I have to pick 6? No, I could have picked any number I wanted to add to both sides of this equation. I could have added 325 to both sides of the equation. And if I add it to one side, though, I have to add it to the other side. Guess what the answers to this equation are over here? -5 and 1. I already know that because all I did was add 325 to both sides. So the addition property of equality says I can add the same number to both sides. And I don't change the solutions. The solutions do not change. So I can add the same number to both sides and the solutions do not change, which is awesome because when we solve equations, which you've already done before, you've used the addition property of equality before, you just never called it the addition property of equality. We're just putting a name to it now to say that in mathematics, it is a legal thing to add 6 to both sides of an equation. It is legal to add a -10 to both sides of the equation. Subtraction gets encompassed into here because you have to remember subtraction is really just adding a negative number. So I could subtract 8 from both sides because that's really adding -8. One more solution, should -5 and 1 be solutions to this equation? Well, let's look at this equation here. It's 3x squared plus 12x equals 15. Should -5 and 1 still be solutions to this equation? Well, let me just rewrite what we started with. We started with x squared plus 4x equals 5. Take a second and see how are these two equations related. There's got to be some relationship here because I just didn't make that equation up out of anywhere. What is the relationship between those two equations? X squared, 3x squared, 4x, 12x, 5. Oh, wait a minute. It looks like I did a times 3. It looks like I took both sides of this equation. Didn't I take x squared plus 4x and multiply it by 3? And didn't I take 5 and multiply it by 3? So I multiplied both sides by 3. And I also used the distributive property, but that's okay. That we multiplied by 3 to both sides. Well, take a second and guess what this property is called, saying I can multiply both sides by the same number. Hopefully, you thought it was the multiplication property of equality. The multiplication property of equality. If I have a statement of equality, I can multiply both sides by any number I want, except 0. I can multiply any number, both sides by any number I want, but 0. And I'm going to preserve the solution set. I can multiply the same number to both sides. And the solutions do not change. I can multiply the number to both sides, and the solution set doesn't change. These two properties here are what we use to solve equations, and they're core to what we do in algebra to say, you know what, I want to multiply both sides by 2. It comes back to multiple times throughout the year. I'm going to reference these two properties of equality because they're what let us do our algebraic manipulations that basically set up the course that we're going to be spending our next 179 days with. How amazing. So when working with equations, we can make new ones that have the same solutions. I never want to change the solutions to an equation. That would be bad. That'd be bad news. We want to preserve the solutions, but I want to change the way they look. So we have our distributive property, we know and love. Commutative property, switching the order of things, moving people around. The associative property says that I can change the grouping, and as well as the addition and multiplication properties of equality. Those are kind of new names that you haven't heard before. So without solving the equations, determine if 2x plus 3 equals 13 minus 5x has the same solutions as 4x plus 6 equals negative 10x plus 26. So are these two equations really saying the same thing? Well, okay, 2x plus 3, how am I getting from here to here? Looks like there's a times 2 relationship here. Looks like I multiplied by 2. Well, did I do that here? Yeah, it looks like I multiplied both sides by 2. So I use the multiplication property of equality to multiply by 2. But wait a minute, it would be 26 minus 10x. It looks like these guys switch spots. What lets me say that I can switch the order of things? That's the commutative property. That's the commutative property of addition. I can switch the order in which I'm adding things. So instead of doing 13 minus 5x, I did negative 10x plus 26. I switched the order there, as well as multiplying by 2. So do they have the same solutions? Yes, they do. Why? Because I used the multiplication property of equality and the commutative property of addition. Using those two properties, I know that this value of x that makes this one true also makes that one true. They have the same answer. They have the same solution.